I'm going to talk about, my talks overlaps with Brian's some, but it'll give you a binocular vision or stereo sound of why music sounds good. So basically, we like when things line up. We like when things form patterns. This is synchronized swimming. And our ears are amazing in their ability to form patterns. We can actually hear a fundamental tone just from the overtones. If you take the fundamental tone out of music and play the music, we can still hear what the fundamental tone was. So going to start with physics, everything that interacts, it exerts a force on each other. And those forces form springs. A small displacement is linear, so it's basically a spring. Everything is made of springs. Every piece of matter is a spring. And a lot of things, if you hit them, you'll hear a sort of a musical note, donk, because everything vibrates like jello. Even a hunk of concrete will vibrate like jello a little bit. And air vibrates very well. It's almost a perfect spring. And your throat is full of air. So Brian talked about frequency. Frequency is how often something happens. And if I push on the air, I'm actually making sound waves right now. Can everyone see my hand? Can you see the motions I'm making? Well, yes. I hope so.
Yes.
Cool. So if you have something that tends to vibrate, as everything does, and you push on it periodically, even if you push like once in every 3 vibrations, you'll still be amplifying it. So imagine that these lines are guitar strings or piano strings. The middle can go up and down, but also the left side can go up while the right side goes down, and also the outsides can go up while the inside goes down, and they counterbalance. Every different airspace in your throat vibrates at a different frequency, and as you shape your throat to make the vowels and to make the overtones and resonances, you're controlling which of those vibrations comes out more strongly. Now, the ear can hear a factor of 1,000 different frequencies, and your ear can hear a factor of 1 trillion sound intensities, meaning the amount of energy that's put into the air. So this is me singing ah, and this is me singing ah, but actually that's not quite true. Here I was singing with overtone, okay, I'll just skip that. So the first harmonic, ah, ah, is an octave. The third harmonic is 2 octaves, ah, ah. But in between, there's 3 times the frequency, which is a perfect fifth. Now, the harmonics here from the major chord, the fundamental ah, 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 the third number goes pa, pa, pa. Shoot. I just didn't leave enough time. Ask me about it in the questions. The circle of fifths does not actually come back to where it started. It comes back almost to where it started, 7 octaves up, but it is not quite the same number. So the circle of fifths defines 12 notes more or less, and the Europeans decided, hey, we should be able to divide an octave into 12 equal parts. We come up with a very irrational number. Pianos are indeed irrational. They're tuned, no note in a piano is exactly consonant with any other note. Not to mention which, mechanically piano strings are stiff. Higher overtones are off pitch by a half tone, which I learned in a Wikipedia crawl a couple nights ago. Now, why does a tritone sound so bad? Ah, 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 ah. The overtones don't stack up at all. So in barbershop, we're adding ah, 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 and I've highlighted in orange the extra overtones that line up and make our ears and brains extra happy. So microtuning and blend, you can't do it on a piano. No note on a piano is consonant. A string quartet, since violins and violas and so on don't have frets, you can tune within a few cents of where you want to. And barbershop, when I'm singing barbershop and I'm well in practice, I can not only hear when it rings, I can actually feel in my throat an extra little pulse when I get exactly in line with the other people singing. So it's like my throat is the tunnel I alluded to. It's a musical instrument. It feels like other people are playing my throat and I'm probably playing theirs, and it's just awesome. So barbershop is awesome, way better than pianos, and go out and learn and sing and practice. Thank you. I can't believe that was 5 minutes.
Well done.
That was awesome.
So when you have questions, there's some slides that I would love to talk about more. This one and this one and this one.
Okay, I opened the participants window because we're still sharing, so if you want to hit a hand, Renauta's hand's up.
Thank you, Garrett. Chris, what is the thing that you wish you could tell us the most that you didn't get to tell us?
I wish I could explain how the chord is built out of the overtones transposed a couple octaves. So the fifth of the series of overtones, if you take it down a couple of octaves, that is the ah interval of a major chord, and actually earlier overtone taking down one octave is ah. So this is almost 1.5, almost 1.5 in the equal tempered piano scale, and the third is within like 1%, but the seventh is several percent off, and you can hear that. So when you're building a chord on a piano, you are never building an actual resonant chord. But if you sing it well, then the overtones stack up, and there's a 12 here and a 12 here and a 20 here and a 20 here, and it just makes your brain really happy to hear it.
Cool, thank you.
So I'm curious to kind of carry that line of thinking. You mentioned that the overtones in a piano can be off by as much as like a half. So does our ear just compensate for it? Like because they're the same on a piano, it still sounds good, and that's why it sounds better when it's barbershop because it's actually on?
Yeah, our ears can compensate for a lot. And there's auditory illusions just like there's optical illusions, and especially if we're trained to the music, if we're accustomed to hearing it, we can kind of fill in how it should sound. So we're also used to pianos that we hear it as a satisfying chord. That's not too bad. I mean, the phases almost line up. The vibrations almost come around and make a circuit.
I've noticed that's actually when I use an open tuning on the guitar, like if you have two notes that are supposed to be the same but octaves in your, like 4 frets up and an open note, like they almost never actually sound in tune when you're trying to play those two notes together. And it's like no matter how you tune it, you can't go up on the string and actually have it sound good. It's like playing with a capo or something.
Right. Guitar frets are equal tempered, the same as a piano. So you can tune the strings to be a perfect fifth apart, but then when you go up on the frets, you're not being the perfect fifth again.
Why is that? Why do they do that?
Well, they do that because, let me go to the circle of fifths slide here. You start with C, and then you go up a fifth, ha, 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 and then you go, ha, which is like, ha, 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 ha. And then you keep going around, and eventually, after doing that 12 times, you get back to something that's almost C. And so the circle of fifths, which is very useful for European style music where you've got lots of chord progressions in it. Not just one chord, but a chord that leads to another chord that sounds nice in sequence that leads to another chord. These 12 notes that are defined it's really nice if the first C equals the last C, but it doesn't. It's off by like almost 2%. 129.7 versus 128 difference. So to make it line up, they just squish all the intervals. Yeah, they squish all the intervals, and the third is actually squished more than the fifth, because the third you have to drop 2 octaves. So the first harmonic is an octave. The second harmonic is a perfect fifth, but the fourth harmonic, 5 times, that's 2 octaves plus a bit. That's the major third. So the third is starting to shift more and more as you try to make it fit the equal tempered scale, where every half tone is exactly a 12th root of 2 apart. So that 12 half tones multiplies into a doubling an octave.
Interesting.
Now, an octave is a fundamental physical thing, as you can see in my overtones slide. These are physical vibrations that my voice was making, and each of these is an octave above the other. So when I'm not singing in falsetto, that was the word I was missing, falsetto. When I'm not singing in falsetto, my voice is making 7 different octaves at once, and you can hear probably all of them. When I am singing in falsetto, my voice only makes like 2.5 or 3 octaves. And this is one reason why I really favor mixed gender barbershop, because men singing falsetto in tenor, they have some overtones, but not a lot. Not a lot.
Cool. Any more questions?
Jamie had one, but it won't
I
let
have a
him.
question. Yeah, something about being a host on Zoom. So I was hoping you could, Chris, explain go back to the chart, or go back to the slide that has like the 4 and then the 5 and then the 6. Either of those? I think you had 2 of them. No, the one that has like a bunch of numbers going straight across.
This one?
Yeah. Can you walk through what this is saying kind of slowly? Because this is something that's really interesting, but I don't even feel like I totally get it that well. I'm just curious what you're talking about.
So if I sing a note like that has a certain frequency, and we can call that frequency 1, or we can we can say to is 1 to 1.25, and we can say to is 1 to 1.5. But it's just as easy to say that is 4, and then ratio-wise, is 5, and is 6, and is 7. That is the ratio of those frequencies. 400, 500, 600, 700, and this would be 800. This is the octave of the 400. I'm not actually singing 400 cycles per second, but pretend I am. Now, when I sing my voice contains this sound, and this sound, and this sound, and several octaves higher that I can't sing, but your ear is capable of hearing, although I up to 20 kilohertz. And when I sing when someone else in my barbershop quartet sings the then they're also singing this and this and this, because spaces in their throat, air spaces in their throat and nose and so on are resonating with those higher, just like pushing on a swing. If you push on a swing that's shorter and you push on it once every 4 times that it goes back and forth, you'll still accelerate it. And then the lead sings and is singing all these notes at once, and the tenor sings and is singing all these notes at once. Now, the reason I highlighted them is the lead who's singing I'm sorry, the bass is singing ah, and the baritone is singing ah, but they're both singing this note, and they're both singing this note, the 20 and the 40, and the lead who's singing ah is also singing ah, and the bass who's singing ah is also singing ah. And so this is just a list of the overtones that everyone's voice is producing, unless they're singing falsetto, in which case they only get the first three. But your brain can fill in the rest. So this is a diagram of how the overtones and harmonics in each person's voice stack up in a barbershop chord, and how they duplicate from singer to singer.
Awesome. Thank you.
Nice. So with the falsetto,
Yeah.
is that because like you're closing off part of your throat and that's why you get less resonance?
I'm not sure exactly what happens, and actually I only have a sample size of 1 to say you just don't get a lot of harmonics on falsetto, but it never sounds satisfying to me when I hear a man singing falsetto tenor barbershop.
Yeah.
So it's possible that like OC Times tenor could get more overtones singing falsetto.
For folks that don't know what those two groups are, could you just quickly say why that would be?
Sorry. OC Times is like a world champion barbershop quartet. So I don't want to say that the tenor of OC Times would be as limited as my voice print here, but I still suspect there would be some limits. I've actually in late night conventions, I've gotten to sing with champion barbershop quartets, and they sound really good, even the tenors. So I don't want to diss them, but at my level, males singing falsetto tenor just
No disrespect.
it's there, but it's not really there.
Awesome.
Sorry?
Thank you, Chris.
Yep.
Yeah, thanks, Chris. That
Sure.
was fabulous.
I'm-
oh.
I just have a question for the general group after that one. Does anybody hear, it sounds like maybe Chris does, but does anybody have perfect pitch where they can actually hear like that, those frequencies like names and notes?
I have good relative pitch. I don't have perfect pitch.
You're darn close, sir. The way you were humming those out, I could tell.
Well, again, that's good relative pitch.
Yeah,
Sorry?
I'm just curious if anybody had like hears some of those differences that Chris was talking about too. Like if it like bothers you more if you have perfect pitch or something.
I have what many have called perfect relative pitch. I can hear up to about 1.7% of a semitone. Like I hear intervals rather than like hear a note and name it. I can hear a note and say that's a third, like hear 2 notes. And like, yeah, hearing that different tuning does change how I perceive a chord, or like, breaking down. In fact, piano notes below like the 2 octave 2, so all of the bottom notes never sound in tune to me, because their upper stuff is actually not in tune. Their upper overtones are not in tune. So it does affect
Because the strings are stiff.
Exactly.
That's cool. So you can hear what he was talking about. That's amazing.
Yeah.